right? And then root 27 is approximately 5 point something, right? So at 5 points, like at root 27 and negative root 27, we have some sort of change from concave up down sort of thing happening. So this is a local max. So my graph looks like this. Should look like this. Okay, so between 0 and root 27, wasn't I concave down? Then once I got to root 27, I went concave up, which is actually going to be my inflection point here. It's going to switch to concave up and head towards my horizontal asymptote. Now we're going to spend more time on this, okay, on the graphing part of it, but I'm just trying to get you to see a little bit ahead here. Here we have a local minimum, right? And I'm supposed to be concave up here, so it's going to look like that. Until I get to root 27, here it's going to switch from concave up to concave down. So it's going to look like that. I'm feeling good about that graph. My computer does not want to graph for me today. Try it again. Okay, it was x over x squared plus 9, right?
Yeah.
There it is. I would argue that my graph's better because I can see more information in my graph than I can see on that graph.
Yours is Hollywood's graph.
Yeah. I mean, you can see that I have a horizontal asymptote here, right? You can see I have a horizontal asymptote here. What you can't tell in this graph is where your local maximum and minimum is. You can maybe guess that it's 3, but you might argue that it's anything around here, right? And then also, you can't really tell where you have a change in concavity, where you have that inflection point. You can't tell from this. Now, I could exaggerate the graph. I could change my window and maybe go from like -1 to 1 on the y-axis, right? So if I start manipulating the window a little bit, I can start to get a better picture. But see, that's why I think this one is so good, because it kind of really illustrates everything, doesn't it? Okay. All right, that's where we're headed. We're headed to this, okay? We're headed to this part. And I'll give you like more of a formal process. But all the setup for it is basically everything we just did. First, second derivative, set them both equal to 0, figure out where they're undefined, test points on a number, or number line, test points, plug in, and then there will be some additional stuff. But shall we try a different function? Yes, of course. That was still a relatively nice function because that's something we've seen in the past, isn't it? So I know Hugo's sitting over there going, why do we need this? If we have a computer, right, that can do this. And my same answer is going to come back to process procedure. You know, are you able to follow a process and understand how everything is connected and not make mistakes, right? Not make mistakes. Do something more advanced, I guess. See, I do a lot of these in the homework, so that's why I'm like not wanting to do this, but yeah, let's try this one. This ought to be fun. F of x equals cosine squared x minus 2 sine x. And we just want this on the interval 0 to 2 pi. So I'm actually restricting our interval because, well, quite frankly, it gets pretty bad if we start looking everywhere at that, as I will illustrate. If we just ask this to graph this, cosine, I know y'all don't like to look at these ahead of time, but cosine of x squared, what is it, minus? Minus 2 sine x. Oh, well, it's periodic. Yeah, so we could do that. It's not bad. But I guess, as you'll see, if we set the first derivative equal to 0, right? We're gonna have every single one of these points. That's an infinite number of solutions. And so how do you do an infinite number of test points, right? It's not really reasonable to do that. All right, so let's do this. Here we go. All right, let's take our first and second derivatives. I think the derivatives might be a little easier than last time, than the last problem. First derivative of this function, same instructions on this one as the last one, okay? Where's it up, where's it going up, down, local max, local min, where's it concave up, concave down, inflection points. So first derivative is, yeah, it's chain rule. So go ahead and do it. What do you get here? You're going to wind up with a negative 2 sine x cosine x. When all is said and done, that's what you're going to wind up with. 2 will come down, 2 cosine, then you take derivative of cosine is negative sine, then comes out front. So there, that good? Okay, no, I haven't done this, sorry. And then minus 2 cosine x. Okay, so that is my first derivative. Second derivative. If you were going to do the second derivative here, you would have to use product rule here, wouldn't you? Right there, you have product. That's your little product. This one you can take derivative by itself. So let's do this. It'll be f double prime of x is derivative of this times this plus derivative of this times this, and then derivative of that out at the end. So what do we have? Negative 2 cosine x times cosine x plus negative sine x times negative 2 sine x, and then plus 2 sine x. Okay, so I took the derivative of this times that plus the derivative of this times that. And then when I took derivative of this by itself, derivative cosine is negative sine, so the negative came out and made that a plus. So we good? Shall we clean that up a little bit? This is negative 2 cosine squared x. Oh, it's plus, darn it. Plus this, I thought this was going to be minus minus, and then we were going to have a Pythagorean identity, but it didn't work. 2 sine squared x plus 2 sine x. Y'all happy with that? Not happy, are you? I mean, is that all right? I mean, can we
factor out a 2 sine x?
You could factor out a 2. But I'm not setting it to 0 yet. I'll deal with that when we set it to 0.
Yeah.
Is everyone okay with those derivatives? Just something real quick that just to show you the way I would have done this. I just thought it was a little too much. I would have rewritten this as, I would have rewritten the original first derivative. I would have noticed that 2 sine x cosine x, that is the same as sine 2x. That's a double angle identity from pre-cal, because it's easier to take a derivative of this than it is to do the product rule. So if I did the derivative of this, it would have been negative cosine of 2x times 2 using chain rule, taking derivative of what's inside, and then plus 2 sine x. That's what I would have. That's what I would have done. Now, it's okay if you did this. I mean, that's what I showed. But how in the world is this equal to this? Well, it turns out that you could use your double angle identity and take cosine 2x back to cosine squared x minus sine squared x. That's the double angle identity for cosine. So you wind up with the same thing, all right? I'm going to leave it like that. Okay, we good? Now, let's find the critical numbers for the first derivative. So we're going to take the first derivative, set it equal to 0. So the first derivative was negative 2 sine x cosine x minus 2 cosine x equals 0. I have a GCF there. GCF is negative 2 cosine x. When I pull a negative 2 cosine x out, I'm left with sine x plus 1 equals 0. And now I set each of these equal to 0. So I set negative 2 cosine x equal to 0. I set sine x plus 1 equal to 0. This means cosine x is 0. This means sine x is negative 1. This is where you would get your general solutions from. If we had not cut this interval off, then back in pre-cal, I think I said this last time. I know with my pre-cal class, I taught them how to get general solutions for this. But we only want the solutions between 0 and 2 pi. So where is cosine 0? Cosine is the x-coordinate, is that correct? So that happens here and here. And so we have that the angle x has to be equal to either pi over 2 or 3 pi over 2. Those are our two solutions for that one. And then where is sine negative 1? So where is the y-coordinate negative 1 here? Right down here. But we've already got that answer here, don't we? Again, if this is like still bothering you, like how I'm getting this, come see me. I did have a student come see me about that, and I think we made it make a little more sense. I'm going to graph these. Make sure you put them in the right order. And now I have a partition. I have 3 different regions, and I pick some points. And the points I pick, I want to keep in mind that whatever test points I pick have to be plugged back into the first derivative, right? And the first derivative, right here, that first derivative has trig functions in it, doesn't it? So I better pick something that I can evaluate easily. So I'm going to pick things that are like with pi's in them, all right? So something to the left of pi over 2. How about pi over 4? You can do pi over 6. You can almost look at it this way. You're trying to pick something between 0 and pi over 2, right? So you pick pi over 4. Now I need to pick something between pi over 2 and 3 pi over 2. So how about pi? Okay? And you don't have to get it in the right position. Just make sure it's between there. And then something bigger than 3 pi over 2. 2 pi, right? And 2 pi is in the interval, so it qualifies. You wouldn't want to pick 3 pi because it's outside. All right, so 2 pi. We could have picked 0 over here, but I liked pi over 4. And those go into the derivative. So let's do it. All right, I'm going to run out of room, so I'm going to do it here. I want the derivative evaluated at pi over 4. I want the derivative evaluated at pi. And I want the derivative evaluated at 2 pi. All right. Here we go. Into the derivative. Negative 2 times sine, right? What's sine of pi over 4? Root 2 over 2. Times cosine of pi over 4. Root 2 over 2 again. Minus 2 times cosine of pi over 4. Root 2 over 2. Now, unfortunately for this one, we can't do plus minus because we don't have multiplication. Like this is subtraction, right? It's this minus this. And with subtraction, it's not as easy. Right? If I tell you I have a positive number and I'm going to subtract a negative number, you can't tell me if that's positive or negative. You can't. You would have to know how big the numbers were. All right? Or if I add these, you can't tell. So, all right, next. Figure it out, right? So what is this? Well, this actually does turn out to be negative because this all together, you get root 2 times root 2 is 2, times the 2. It's 4 over 4. This is negative 1 right there. And then minus, these 2's cancel, so you just get root 2. So negative 1 minus root 2 is negative. Y'all good? That means the original function over here is going down. It's one of the worst pi's I've ever put on the board. There we go. There's pi. F of pi. F prime of pi, sorry. So negative 2. What's sine of pi? 0. Times, what's cosine of pi, even though it doesn't matter right now? Cosine of pi is negative 1. Minus 2 times cosine of pi again, negative 1. So this goes away, and that's just 2. So you get a positive there. So F goes up. And then plug in 2 pi. I'm pretty sure it's going to go down, but we'll check it. Negative 2, sine of 2 pi is 0. Cosine 2 pi is 1. Minus 2 times cosine of 2 pi is 1. So you get negative 2. So it goes down. All right, I think I'm not going to write down the conclusion. I'm going to let you do that because this is all we need, right? From this, you can tell me where it's going up, where it's going down. You can tell me where we have local max and local min. So can I move on to the next part? Okay, let's do the second part, which would be the second derivative. Oh, we never checked where the first derivative was undefined. That's my mistake. But I guess I had already thought through it, you know? I mean, like, these are cosine. There's no division by 0. Like, there's no problems here. Okay, so let's move on. Second derivative equal to 0. Is the second derivative ever undefined? No, it's perfectly fine. This is a perfectly well-behaved function, no division by 0. Now, if it had, like, secants in it or something, yes, we'd have problems. Secants or tangents or cotangents or cosecants, because those things have domain problems. Okay, second derivative equal to 0. Negative 2 cosine squared x plus 2 sine squared x plus 2 sine x equals 0. And how about I divide everything by 2? Just to get rid of that 2. Is that all right? Gone, gone, gone. Okay, the next step is really a function of whether or not you understood this in pre-cal, how to solve something like that. That looks a whole lot like a quadratic equation, doesn't it? Except that you've got cosines and sines. So why don't we get everything either in cosine or everything in the sine? What do you think we should go with? Sines? Because we got sine here, sine here. Is there any way that you can rewrite cosine squared x in terms of sine? What is it? So this negative, let's just bring it down. Cosine squared x is 1 minus sine squared x. That I'm getting from the Pythagorean identity. And all I'm doing is I'm solving it for cosine squared, so I'm moving this over to the other side. And then we still have plus sine squared x plus sine x. Do you remember last class I told you the 2 things that I tell my pre-cal students I need to know? The unit circle and solving trigonometric equations. That's the 2 main important things. All right, now let's keep moving with this. This is negative 1 plus sine squared x plus sine squared x plus sine x equals 0. Now it's looking a lot more like a quadratic. I can combine these 2 sine squares together to get 2 of them. So I'm going to put it kind of like in a descending order now. Now it looks a lot like a quadratic, doesn't it? And I'm going to hope it factors. Do y'all know what I mean by this looks like a quadratic? Like if you replace sine with u, this looks like 2u squared plus u minus 1 equals 0, and then you try and factor that. And what would that be? Does it work? 2u, u, I think I'm going to need plus 1 minus 1. I think that'll make it work. That's what it would be, right? Get 2u squared, 2 plus 2u minus u, and then minus 1. Yeah, that works. So for us, it's not 2u, it's what? 2 sine x minus 1, and then sine x plus 1. Now you set each of those to 0. So if I set that to 0, that really turns out to mean sine x is a half. Like once you set it to 0 and move the 1 over, divide by 2. And this one is sine x is negative 1. So now we just need to go over a unit circle and figure out where this happens. Yeah, so where is sine a half? That's your y coordinate. It's a half here, and it's a half here. So I heard pi over 6 and 5 pi over 6. So at pi over 6 and at 5 pi over 6 is where the y coordinate is a half. And then here, where is it negative 1? Where's the y coordinate negative 1? 3 pi over 2. Whew. All right. Now what? Plot them out on number line. And remember, we're between 0 and 2 pi, right? Just keep that in mind. We can't go outside of that. Pi over 6 would be somewhere over here. 5 pi over 6 here. And 3 pi over 2 somewhere in there. You're okay with the order of those? All right, pi over 6, 5 pi over 6, and then 3 pi over 2 is down here. So that's the order that they're in. So what would you like to pick as, oh, I didn't partition, sorry. It's only partitioned here, here, and here. Remember, this is just where we stop, right? We're not allowed to look over here. We're not allowed to look over here. So what's a good number over here? Ooh, we don't have a common one, right? So let's go with 0. Okay, we're going to go with 0 for our test point here. How about here? Pi over 4? Pi over 2? What do I? Yeah. Here's pi over 6, right? That's 5 pi over 6. We could use pi over 4. We could. Pi over 2 is nice, though, isn't it? Pi over 2 straight up. Let's do that one. Pi over 2. And then anything after 5 pi over 6 and before 3 pi over 2. So pi. And anything after 3 pi over 2, 2 pi? You want to go with the endpoint? Where are those getting plugged in? To the second derivative. We're almost there. We're almost there. This one seems like it went a little faster. What's that? Yeah, I skipped a little bit, didn't I? I didn't write the final answers down. But, all right, I'm doing second derivative at 0. Second derivative at pi over 2. Second derivative at pi. And lastly, second derivative at 2 pi. Had that panic that I never unmuted my microphone, but we're good. All right, plugging in to the second derivative, which is here. And trying to determine what the sign is. So if we plug in 0, negative 2, what is cosine of 0? Cosine of 0 is 1. Square it, so still 1. Plus, okay, sine of 0 is 0. Squared 0. So that second one is 0. Is that all right? And the last one's 0. So you just get negative 2. What does that tell me is happening in this first little region between 0 and pi over 6? Concave down. So F is concave down. Now pi over 2. Negative 2 times, all right. What's cosine of pi over 2? So cosine of pi over 2 is straight up x coordinate 0. Squared, so that's 0. Gone. And then plus 2 times sine of pi over 2 is 1. Squared is 1. And then plus 2 times 1 again. So this is going to be a positive number, right? 4. I know you just want to say, hey, they switch, right? They're just going to alternate. I know you want to say it. But trust me, we'll do an example, not today probably, where they don't. Plus, how much fun is this, right? Yeah. Getting to plug these in again and go back to the old days, pre-cal. Isn't this great? Okay, negative 2 times cosine of pi. Careful. Cosine of pi. Negative 1 squared. 1. So that still turns out to be 1. Be careful with that. Here, I'll even put it here. It's negative 1, but it's squared, so it's not going to matter. And then we're at pi. Sine of pi? 0. So those last two are 0. So what do we get here? Negative 2. So it's concave down. So yes, it is switching. And finally at 2 pi. Shouldn't we get the same answer we got at 0? Because 0 and 2 pi are basically equivalent angles, so we should get negative 2 here. Oh, whoa. Hey, it didn't switch. It didn't switch, did it? Ah, good. Still down. All right, that makes me happy now. We're done. I'm not going to write the answer down. Is that all right if I don't? Where do we have inflection points? Pi over 6 and 5 pi over 6. That's it, right? This is not an inflection point. It does not change concavity here.
Sir, can you do the maximums and the minimums? Because I got 0 for those. I don't know if that's
You got 0? What do you mean you got 0?
yeah, like for the maximum, the lower maximum, the local maximum, local minimum. You know how you just plug in power 2 and 3 power 2?
Yes.
I got 0.
You got 0 for those?
Yeah.
Okay, so let me look at the graph real quick. Let me go back to the graph. Yeah, I think the maximums were 0. Okay, so look, this is the graph, right? Let me zoom this in to just 0, 2 pi. 0. I don't know, 6.24. That's close enough. Ha ha ha. Yay. I'm happy to see this. Wonderful. So check this out. So your question was about the, well, can I change those to pies? Step. Yeah, I need to learn this one a little bit more. All right. Where did we have local maximum? 3 pi over 2. So here's 2 pi. Pi is about 3.14. This is pi. Right? So about halfway between these, right in here. That's where we have our local max. Right? And what is the local maximum? You said you got 0? You said you got 0?
I don't know if that's correct. Yeah.
If what's correct?
Like me getting 0. Because I plugged in the power 2 into the
3 pi over 2 or pi over 2?
or 3 power 2, yeah.
Into the original function? Let's plug 3 pi over 2 into this. If we plug 3 pi over 2, we get cosine of 3 pi over 2 squared minus 2 times sine of 3 pi over 2. To the original, to find the max and min, right? So this is 0, and this sine of 3 pi over 2 is negative 1. but then times negative 2 is positive 2. So here it's 2, which you can kind of see it here, 2, that's 2. Yeah? Okay, so we have local, we had local max at 3 pi over 2. We had a local min at where? Pi over 2? So that would be here. And then our concavity, we had some weird points, but let's try and figure out where the concavity changes. So it looks like we are concave down here. And then at pi over 6, somewhere in here, it's going to go from that frown to the smile. You see it in here? Somewhere in here it switches. And then here we're still smiling, and then somewhere in here it switches to the frown. And then it's going to be frown, and it stays frown. Stays frown. So at 3 pi over 2 right here, it stayed frown. Is what it is. What do y'all think? Huh? So we have our test a week from today, so what we'll do next class, we'll do more of these, all right? And please come with any questions that you have over, I'm not ending class, hold on, I want to talk about one last thing. But come to class with any questions that you might have over any of the stuff that's going to be on the test. And what is going to be on the test? We are going to have everything since the last one. So, oh wait, did I grab the wrong one? I grabbed the wrong one. Darn it. I was going to bring your work for you so I could hand it back to you, and I grabbed the wrong folder. I'm sorry. Bring it next time. Okay, well, just look at the material after last test, right? That's what's going to be on this test. Up until this section 4.3. I do not think I'll go past this, right? Because think about it. I'll give you one of these problems. It's going to take you at least 20 minutes, right?
The whole test should just be 2 of these.
2 of these for the whole test? Okay, I'm going to draw a picture for you real quick. Because the inflection point, I want to just talk a little bit about the inflection point. Let's just say for the sake of me demonstrating this, that you have a company and you're looking at your profit over some time period in the past. And you have this sort of scenario going. Like let's say you started your business and your profits did this, and this is where you are right now, okay? This is present day. You can say that your profits have been increasing, haven't they, over time, right? Do y'all see an inflection point anywhere? Do y'all see an inflection point? That's where it would switch from concave, like the concavity would change, either from concave up to down or down to up. Y'all do see it? Okay, so that concave switch is happening somewhere around here. Do y'all see that? That's where you're going from the smile to the frown. So something happened here. That's when we hired Jason. He's not here, so I'm going to pick on him today. So that way if he watches the video, he can get a kick out of it. Okay, so we hired Jason, and then this happened, right? And so we're still making money, right? But what? What about it? Yeah, it's like, look, when we're here, we're increasing here, right? So here we are, our derivative is positive, and our second derivative is also positive, right? So we're increasing, making money, making profits going up, right? Here, our first derivative is positive still, but our second derivative is now negative. So compare now, the way I want you to see this is I want you to compare the tangent lines. Look at the steepness of this line, okay? Steeper, 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 steeper. And then once we got here, I'm still positive, but what? Less steep, right? And so what's happening is the rate at which our profits are increasing has dropped. So here our profits were in the rate at which they were increasing was going up. So as time went on, we were making money faster. And then we got to this, and we're still making money, but not as fast as we were making money. This point in a business model like this is called the point of diminishing return. The point of diminishing return. You're still bringing money in, but at this point, that the money that you're bringing in is starting to diminish. That's an important point in a business class or a business model. Your point of diminishing return, if there is one. You don't want one, but if there is one, you would want to go back and look at like what happened here. We hired Jason. Well, that explains it. That explains everything. Okay. All right. So you know what to do over the weekend. You've got those 3 problems. I would suggest you try and knock those out this weekend, or get completely caught up on the homework. One or the other. Don't leave those problems till the day before the test. Have a good one. Huh? If you came in late, I handed out some problems. Anyone else? You got an extra? Just please change this date to the 11th, not the 12th. Those are the take-home problems that are due next week for the 3. There's, to the 11th.
Are you going to have office hours right now?
I am, yes.
Can I ask you a quick question?
Sure. Let me turn off my camera and stuff. Oh, hey, if y'all want help on those word problems, you